Hello and welcome back. Today we're going to be talking about the equilibrium and Newton's second law. The equilibrium force is going to be a real simple one. So if I've got two forces on an object, then it's stationary. It doesn't say stationary, but let's assume it's stationary. Then the sum of the forces in the x have to cancel out. Oh, it's just not stationary. I'm sorry, I had a brain fart. There's no forces left or right, so the sum of the forces left or right are 0. Some of the forces up and down are not going to be 0. It's going to be 10 minus 15. We're going to have a net force of negative 5 newtons. So the net force is minus 5 newtons down. So it would behave as if there was a 5 Newton force pushing down on it. Those two forces could be replaced by one force and it would have the same net effect. If I've got these two forces upwards at an angle, so we've got a net force in the x and y direction. Now, if I wanted to add these two forces and figure out what the total net force was, I could use Pythagorean's theorem again and sine cosine tangent, and I could get 18 newtons, 34 degrees north of east. And I could replace those two forces by one force like this one, and it would have the same net effect. So this connects with what's called the equilibrium. Basically, no matter how many forces you apply on an object, that are applied to an object, you can cancel all of those forces out with one single force. And that single force that cancels out all the other forces is called the equilibrium force, because it establishes equilibrium. So if you've got, start out really easy, if you've got a force of 10 newtons to the left, the equilibrium force is 10 newtons to the right. Okay, if you've got a force of 15 newtons up, the equilibrium force is 15 newtons down. Okay, if you've got a force or forces that add up to 20 newtons, 30 degrees north of east, again, it's just the force is equal and opposite the resultant force. So here we've got all these forces, force 1, 2, 3, and 4. If I want to figure out the single force that'll cancel those out, what I do is add them up, and just like adding vectors, you just add up your x's and your y's and your whatever and figure out the net force. And this is my resultant force, so my net force. The equilibrium is just something opposite that. Okay? So if I want to figure out the equivalent force of 10 newtons and 10 newtons, I would add these two vectors up, and I would get, I'm pretty sure, 14.1. I wasn't planning on doing this one, which is why I don't have it. Second root, second answer. Yeah, so it's 14.1 at an angle of 45 degrees. So my net force would be 14.1 at 45 degrees. So my resultant force, my equilibrium force, my equilibrium force would be exactly opposite that, and that would cancel these two forces out. Okay. When we apply a force to an object, it accelerates. But not all objects accelerate at the same rate, even if the same force is applied. If I were to apply the same force using a leaf blower on a tennis ball and a bowling ball, okay, the result is going to be a lot more noticeable on the tennis ball as compared to the bowling ball. That is because the bowling ball has a lot more inertia, and what gives an object inertia? Its mass. Okay, so this is Newton's second law, and that is equal to the force that is required to accelerate an object. The force on an object is equal to the mass times the acceleration of that object. And by force, we're talking about the net force. The net force is equal to the mass times the acceleration of that object. Okay, F equals ma, Newton's second law. So they're proportional. Now, this is not the definition of a force. A force is a push or a pull. This is a relationship. Basically what this tells me is if I want twice the acceleration, I need twice the force. If I double the mass, I'm going to have half the acceleration, that kind of stuff. So it's a relationship. The units on it would again be mass, which would be kilograms, times acceleration, which is meters per second squared, and we would get kilogram meter per second squared, also known as a Newton. Okay, so rearranging this equation into solving for acceleration equals force divided by mass. So if you increase the force, you make the top of this bigger. What happens to the acceleration? This side gets bigger if this top gets bigger. So if you increase the force, you get more acceleration. If you increase the mass, then this side of the equation gets smaller, and since it's an equation, this side gets smaller as well. So that means if you increase the mass, you get less acceleration. So it's a relationship. So equal forces applied to a chipmunk and a elephant who's in a skate club. You get a lot more acceleration on that chipmunk, okay, which is very practical knowledge about the chipmunk and the elephant. Now, using Newton's law to explain free fall, if you drop a 1 kilogram and a 10 kilogram mass, okay, they hit the ground at the same time. We established that from the previous unit. Okay, so when we're looking at this, what's accelerating these objects is their weight. Okay, now this mass right here is 10 kilograms, so it's got 10 times the weight of this 1 kilogram mass. Since this thing has 10 times the force applied to it, shouldn't it have 10 times the acceleration? No. Okay, because it also has 10 times the mass and 10 times the inertia. So since A equals F over M, okay, and when I multiply the force times 10, because the mass is multiplied by 10, we get the same acceleration. Okay, that's why all things fall at the same rate, you know, and without air resistance. Okay. So a 5 kilogram object, or sorry, 3 kilogram object has a force of 250 newtons pushing it forward and 650 pushing it back. What is its acceleration? So this is the case when the forces are not going to be balanced. Okay, so when we look at, instead of saying 0 equals blah blah blah, it's going to be mass times acceleration equals, because the F net equals mass times acceleration. So that's Newton's second law. This is the MA part, and this is the F net part. So F net equals 250 minus 650. So plugging in for M, 3, you get 3A equals negative 400. So my acceleration is equal to minus 133 meters per second squared. Okay. This is I've got a tennis ball cannon in the classroom. Originally it was a golf ball cannon, but that proved too deadly, so we converted it to a tennis ball cannon. And so this is some real data that we took on the tennis ball cannon. So tennis ball launches a 57-gram tennis ball from rest to 27 meters per second in a 93-centimeter barrel. What's the average force acting on it? Okay, so I want to know the force, which means I'm going to be using F equals ma. Okay, now I know the mass is 57 grams, or 0.057 kilograms, but I need to know the acceleration. Going back to the first unit, we know that it gets to a final velocity of 27 meters per second starting from rest, and it does so in the length of a displacement of 0.93 meters, 93 centimeters, barrel. So we get the acceleration is 392 meters per second squared. So that's pretty many meters per second squares. Once we know that, then we can plug it into F equals ma, and we get 22.3. Okay, so what we're going to do is figure out the acceleration on the boats here. So let's see, A equals m, or F over m. So F over m. So F and m. So my acceleration is going to equal 1 meter per second squared. Okay. Now F over m. Now my acceleration is going to equal what? A half a meter per second squared. Okay. What's my acceleration going to equal here? 0 meters per second squared, because these two forces cancel out. What's my acceleration going to be here? 2 meters per second squared. So this one is 2 meters per second squared. Okay, what about this one? 100 and 200 going 200 going to the left. That's going to equal minus 1 meter per second squared because it's going to be negative. Okay, and what about this one? This one, 100 squared plus 100 squared equals 141 squared. So so basically the net force would be equal 141 newtons down and to the right. So the acceleration would equal 1.41. So so net force equals mass times acceleration. So if the net force is 0, then the change of velocity is 0. Okay. Here we got old Bessie. Old Bessie's a cow, and we want to lift her up. She needs to get to the second story of my barn. Don't ask me why, but old Bessie needs to get to the second story. So what we are going to do is we're going to accelerate her at a rate of 1.85 meters per second squared. And old Bessie has a mass of 911 kilograms. So what we want to do is figure out the sum of the forces. So first off, we know there's going to be a force of gravity down. Okay? There's going to be a force of tension up. Now I'm going to draw the tension up a little bit longer because it's accelerating upward, so I know this is going to be a little bit longer. It doesn't really matter because it's not going to end up affecting your problem if you draw this longer or shorter, as long as you do everything else right. But it's kind of a good way to help make Sandy check things. Okay, so now what we're going to say is the sum of the forces. I'm sorry, so we've got gravity down and we've got the force of tension up. We also have a dog who's very upset at something. Something very scary was outside apparently. I had to pause the video for that. Okay, so and we've got the force of tension which is going up. Okay, all right. So what we're going to do is we're going to solve. We can ignore our x forces because there are none. So we can ignore the sum of the forces in the x. But if there were x forces, they would cancel out if it was accelerating upward. So now we look at our y forces. So we're going to say the net force ma is equal to ft minus fg. So Fnet equals Ft minus mg, and Fnet equals mass times acceleration. So plugging in for Fg, not plugging in for Fg, solving for Ft, and then subbing in for Fg, mg. So I should have probably shown that step here, but and then pulling out m. So Ft equals m times a plus g. And I'm going to want you to be able to solve these in terms of variables without numbers at times. It is good for you to do that. It's a little bit more realistic as to what will happen on the AP exam, but they're more likely to want you to do something like that than it is solve a straight numbers problem, probably. So, but we'll do both. Okay, so at this point, I plug in the mass is 911 kilograms. And the acceleration is plus 1.85 meter per second squared. And gravity is 9.8. So sticking those in and multiplying by the mass, you get 10,613 newtons would be required. Okay. Now, how much tension in the rope is going to be if Bessie is accelerating downward at 1.85 meters per second squared? Well, basically I would know that this one would be shorter now. Okay, how is that going to affect this? Fnet is still going to equal Ft minus Fg. Okay, so when I go to plug in my numbers, so the key thing here is when I plug in this 1.85, what's critical? How am I going to say that it's pointed downward as opposed to upward? I'm going to make it negative. So minus 1.85 plus 9.8. Okay. And then how much tension is in the rope if Bessie is traveling downward at a constant 1.85 meter per second? Okay. So we're going to use the same equation. It's the same problem, just changing it up a little bit. what's the acceleration? How am I going to figure out the acceleration in this last part here? Well, there is no acceleration. So A equals 0. So Ft equals mg. Okay? Alright. I've got 2 more problems. And that is all we got today. Okay. So here we've got a crate. It's being pulled. We want to figure out. Oh, I think I forgot to find the acceleration. So we've got a crate that's being pulled by a rope, 15 degrees, strug along the ground. There's a frictional force of 26 degrees to the left, or 26 newtons to the left. The box is only moving parallel to the ground. Determine all the forces on the crate and its acceleration. Okay, so this is 124 newtons, and this is my 15 degrees. Okay, that's probably quite a bit more than 15 degrees, but it doesn't have to be to scale. We've got our normal force, which is up. Don't forget that there would still be a normal force. We've got a frictional force of 26 newtons of friction to the left, and we've got a force of gravity down, which is m times g, equals 230. Now I'm going to go ahead and break this diagonal into its components, which is when you get a problem that's got diagonal vectors, you're going to more than likely break them apart. So here we've got, this is the sine, which is 32, and this is using the cosine, which is 120. Alright, so the first thing we want to do is we can say that the forces in the y direction cancel. So, but not the forces in the x, because we said it's moving only parallel to the floor, so it's not accelerating up or down. So we can use our 0 equals, okay, Fn, which is up, okay, plus 32, which is up, minus 230, which is down. Okay, and we get the normal force is equal to 198 newtons. Okay, now here we're going to say that the sum of the forces is not equal to 0, it's just mass times acceleration. So ma equals 120 newtons minus 26 newtons, so equals 94. So 23.5, so mass times acceleration, so 23.5 times the a equals 94, and we get equals 4. Okay. Let's see. Last question. So here we've got a 45 kilogram crate. You might want to take a break and come back to this if your brain's getting too zoned out. But this is the last question. 45 kilogram crate sliding down a frictionless hill. Okay. The angle of the slope is 34 degrees. What's the crate's acceleration? So what we want to do, since we're on a hill, okay, we're probably going to end up breaking it. We're going to be rotating the page. Okay, so we're going to rotate the page. So here's my force of gravity. I draw straight down. All right. Then you can draw your normal force perpendicular to the slope. Okay, and then your force of gravity in the y is parallel to the normal force. And your force of gravity in the x is parallel to the slope. Okay, and we know that this angle is 34 degrees. Okay, so we know that these two forces are going to cancel, and what's going to be left over is this FGX. So solving for our sum of our y direction, the forces in the y direction cancel, so Fn equals Fg. The forces in the x direction do not cancel, and we're going to have mass times acceleration, since the forces do not cancel, equals Fgx. So mass times acceleration, and Fgx is going to equal the sine, the opposite sine of 4 times 441, because we know the hypotenuse, and the acceleration is equals 5.48 meter per second squared. Okay, that is it for today.